On the previous slide, we studied a bunch of logical laws. Now, these are just logical equivalences that are well known and that have standard names. But of course, there are many more logical equivalences. In fact, there is an infinity of them. So let me add a few more on this slide that are very important for you to know. A much smaller subset than the infinite set. So the first one states that P implies Q is logically equivalent to not P or Q. Now, of course, you should be able to prove this logical equivalence and every other one in this course using truth tables. But here, let me give you the intuition for why this equivalence holds. For that, all you need to know is the definition or truth table of material implication, P implies Q. Remember that the only time this implication is false is when P is true and Q is false. On the flip side, P implies Q is true as long as P is false, regardless of the value of Q. And P implies Q is also true as soon as Q is true, regardless of the value of P. These are the other three cases in the truth table. So what this means in particular is that if P implies Q is true, then it must be the case that either P is false or Q is true, because these assignments of truth values to P and Q cover all the cases where the implication is true. Okay, so this one is very important, and I don't know if it has a name, but I'm going to refer to it later with the asterisk. Now, the other thing I want to mention about this logical equivalence is that another reason it's important is because you can always get rid of, or you don't really need the material implication connective, since you can always replace it with a single negation and a single disjunction, in a similar way that we never really needed the exclusive or connective. Here is another example where P implies Q is basically simply a shortcut for this slightly longer proposition. Now, here is an important point that you may or may not have realized, is that in this and previous logical equivalences, there's nothing special about the propositional variables P, Q, and R. In other words, the logical equivalences still hold if you replace these propositional variables with any propositions whatsoever. And that's the reason why there isn't, or one of the reasons why there's an infinite number of logical equivalences, because even if we started with only this one here, we could build an infinite number of them simply by replacing its atomic propositions with an arbitrarily complex compound proposition. So let me show you an example. Let's say I replace P with the compound proposition not P1, and then I replace Q with the compound proposition P2 and P3. And then I connect those with a conditional. So what I get is basically an instance of the left-hand side of the logical equivalence. And therefore, if I perform the same substitutions for P and Q, I will get not P1 on the right-hand side, or P2 and P3. And the key point here is that the logical equivalence still holds. So now I have a new logical equivalence that we inferred from this one, again, because P and Q are nothing special. They just stand for any propositions. So let me justify this new equivalence in blue by saying I obtained it using the equivalence asterisk. And now the cool thing is we don't have to stop there. What we can do is we can look inside this new equivalence and see if some components of it match other logical equivalences that we know. For example, this compound proposition, not P1, actually matches the left-hand side of the double negation law. So we're completely entitled to replace not P1 with P1. So we get a new logical equivalence. Now this one says that this compound proposition is logically equivalent to this one. And you must always justify these inferences by stating the law that you're using. In this particular, I'm using double negation to go from here to here. Well, we might as well keep going. Notice how the right-hand side of this new equivalence matches the left-hand side of the first law of distributivity. In other words, I can distribute the disjunction over conjunction here. And so what we get is another equivalence, namely this compound proposition is logically equivalent to this one, which is the right-hand side of the law that we called D1. Now I'm going to stop here, but I guess the main point here is you can always obtain new logical equivalences by replacing equals by equals. And by the way, this has a name. It's called equational reasoning, because your reasoning or your inferences are driven by a sequence of equations, or in this case, equivalences, that allow you to prove, in this particular case, that this original proposition is logically equivalent to not only this one, but also this one and that one. The next logical equivalence is one that you already worked at in a previous lecture. It states that if you start with a conditional P implies Q, and you take its contrapositive, not Q implies not P, you get a logically equivalent proposition. Again, nothing new here. The next one is new. It says that the negation of P implies Q is logically equivalent to P and the negation of Q. So first, let's work out the intuition for why this logical equivalence holds. It's always a good idea to go back to the definitions. If you don't know how to start when solving a problem, it's always a good idea to go back to what you know, the basics, the definitions. Now, in particular, what is the definition of material implication? P implies Q. We know that it's false in only one case, namely when P is true and Q is false. So what the left-hand side says here, it is not the case that P implies Q. In other words, P implies Q is false. Therefore, it must be the case that P is true and Q is false. And that is the intuition why this logical equivalence holds. Now what I want you to do is to actually prove it. And I want you to do it in two different ways. The first way is well known to you, but doesn't hurt to practice it, is use the truth table algorithm to prove this logical equivalence. The second way I want you to write the proof is to use equational reasoning. And so my suggestion is to start from this logical equivalence and maybe put parentheses around the left-hand side and then put a negation in front of it. Of course, if you do that, to maintain the equivalence, you need to add parentheses and a negation on the right-hand side. And it won't take you many steps from there, equational reasoning steps, that is, replacing equals by equals with known logical equivalences for you to reach the right-hand side. Please solve this problem as completely as you can, and let me know if you have questions. So I hope that you worked really hard on this problem, and if you need more practice with equational reasoning, we will do another example on the next slide. But for now, let's go back to our list of important logical equivalences. The next one is not only intuitive, but I'm pretty sure we discussed it before. What it says is that if it is true that P biconditional Q, then it must be the case that not only P implies Q, but also Q implies P, and vice versa. Right? If this is true, then this must be true. The logical equivalence works both ways, right? These two propositions are always true at the same time and always false at the same time. So let's move on to the last logical equivalence for now. And what it states is that if it's not the case that P biconditional Q, in other words, it is not true that P and Q have the same truth values, which is what the biconditional means, then it must be the case that P and Q have different truth values. And since there are only two truth values, true and false, it may be the case that one is a negation of the other. And that's what the equivalence says. The equivalence says that the negation of a biconditional is equivalent to the first operand of the biconditional and then the negation of the second operand. Now you might say, wait a second, how do we know that P is not Q as opposed to Q is the same as not P? Well, think about it and you'll see that it's basically the same thing. So this concludes the list of important logical equivalencies that you need to know at the minimum in this course.